Good morning, everyone. Thank you for attending our session about what's behind the 8K video streaming at Cloud Age. Well, I hope you can enjoy our session as well as the splendid scenery in Berlin. And I'm Jinghua, and my English name is Coco. I will give this presentation with Changzhi and Shaohe, while I and Changzhi are both the staff researcher from the Lenovo Research. Shaohe is a cloud engineer from the Intel. Today we are going to talk about 8K video at the edge. Firstly, we will introduce the background of 8K video. Then we will elaborate our edge-optimized architecture, which is based on the Starlink project. Next, we will focus on our work, the work we have done to meet the 8K video requirements, followed with the demo and the summary part. You know, Berlin is a magical city, and 2 months ago in Berlin IFA Consumer Technology Show, it tours 8K TVs that capture the headlines. Big TV manufacturers like LG, Samsung, and the Chinese manufacturers TCL all launched their 8K TVs. And the conception of 8K can trace back to 2012 or much earlier, and these years, and you can the news about 8K can be seen everywhere. Like in August 2006, NHK kicked off the first 8K satellite broadcast, and in March this year, Alibaba released the 8K video cloud solution. Oh, and I think the most well-known one must be that Tokyo Olympics will be held and will be shoot and broadcast in 8K. So we heard a lot of news about 8Ks. What made me think that? What is 8K and what kind of features that 8K have? The answer to this question may be much simple if we compare 8K with other resolution. And the table on the right compares those at 5 dimensions. And the first dimension is the resolution. 8K refers to any screen or display that width is around 8,000 pixels. And so it's 4 times of 4K and 16 times of the Full HD, or we call it 1080p. And you can tell from the left picture that the 8K resolution displays higher picture quality. As for the audio channel, 8K Ultra HD supports 22.2 degree of audio channel rather than the 5.1 channel of 4K. And the 100 degree of viewing angle empowers the user to catch every frame and enjoy their video with immense sense. As for the coding format, 8K used H.265, or we called HEVC, or VP9. Next, for the network bandwidth, to transmit 8K of 112 FPS, network bandwidth needs to reach 120 Mbps. While for the HD and the 4K, the number is much smaller. Great features as 8K have, no doubt it offers even stronger sense of presence and realness to viewers. Hence, the usage of 8K may be well-rounded. One common usage is in commercial TVs. Others like the immense video applications such as panoramic video and virtual reality. Also, in real-life applications such as the healthcare and the high precision monitoring. In the remote healthcare with 8K resolution, doctors can see the internal structures of the blood vessels and the boundaries between the cancer issues and the normal issues. Also, the tiny saturs, which are very difficult to see even with the naked eyes. And the high precision monitoring is needed in the crowded areas like street and airport. To use 8K features, we must first cope with the challenges that 8K video may bring. And the first challenge may come from, every procedures from the camera side to the end user. And the first challenge is the difficulty to manage the cameras in the coming smart city eras, because most of the cameras will be placed separate and far away from data center. Statistics from NVIDIA shows that believes that there are 1 billion cameras worldwide by 2020. And the second challenge came from the more parallel computing of the main coding format of 8K video, like HEVC or VP9. And the third one is when using deep learning or machine learning models to analyze 8K video, it poses a heavy load on data processing because of the high resolution. And the fourth challenge came from the transmission of 8K video, which need 120 or 50 Mbps. To cope with these challenges, first we need edge computing technologies which provide the high bandwidth and low latency. And based on that, we need the different accelerators to empower the deep learning or machine learning models and video codec algorithms. Also, we need to manage the device and the topology of different separated edge clusters. So that's why we came up with our edge-optimized architecture. And in the video scenario, it's suggested that we process the video that at the edge, then send the result to the data center. So we use OpenStack in the data center, and in the edge side, we utilize DarlingX project because it was a very scalable and development-ready edge solution. And it provides fault management, host management, service management, and so on. And that's what we need. But how we cope with the remaining challenges, such as the accelerator management, or how can we manage the topology of different kinds of device? I will introduce Zhi and Shaohe to elaborate that.
Hello, everyone. My name is Jichang Zhi. I am a staff researcher at Lenovo Research. In this slide, let me talk about our edge computing solution architecture. It contains two parts. One part is cloud computing in data center, and the other one is edge computing. In our OpenStack platform, we manage physical networking infrastructures by our internal project. In this project, we can see the network topology and operate switches and servers. I will explain you how it works in next part. At Edge, we use DarlingX as Edge infrastructure software platform. Beyond DarlingX, we do something more on it. First thing is physical topology management. The second thing is edge devices management. We need to manage the life cycle of different Windows devices and monitor them. I will give you a detailed introduction in next part. The third thing is that we use Sepulga to manage our accelerators, such as GPU and FPGA. Shaohe will talk about it later. Both in cloud computing and edge computing, they bring together technologies like Ceph, DBDK, SRIOV, and some accelerators. Both in data center platform, both in OpenStack platform and StarlingX, we are using Ceph as our storage backend. We have done a lot of optimization about the Ceph performance, such as erasure code, online upgrade, and date consistent enhancement. This part, I will give you a detailed description about physical topology management, edge devices management, and accelerators. First, let me show you our physical topology management project. Both in data center and edge side, we can manage our physical topology. At the beginning of the physical topology management in edge, it will be registered to the data center as an edge cluster. Data center will store edge clusters information such as clusters, switches, servers, and links. One data center can own several edge clusters, and every edge cluster will report its status to data center. This project consists of API server and topology process. API server is the entry of APIs. It receives HTTP requests and command line requests. API server returns topology data from DB. Topology process gets topology information by using SMP protocol. We need to set the IP address range of switches before start the topology process. At the beginning of topology process, it will scan all IP addresses which we set before. After scanning, we can get these active IP addresses next. We can connect them and get LLDP information by SNMP protocol. Additionally, if the network topology is changed, this project can detect the change within few minutes. How does this project work? Briefly, we enable LLDP feature in switches and installed LLDPD process in servers. So we can get the whole network topology by running LLDP protocol between switch to switch or switch to server. At last, we use SMP protocol to get the LLDP information, so we can get detailed information about the switches, such as software version, system name, interfaces status. As for our edge devices management, just like Neutron LBus, Neutron FWaaS, edge devices management is a pluggable project. We will design some abstract interfaces, and different vendors who want to use this project need to implement their own driver. Next, we will design camera common plugin and sensor common plugin to fit cameras and sensors. Additionally, new edge devices will be registered into this service, and we can monitor these devices.
Good morning, this is Shaohe from Intel Cloud team. Now let me introduce some hardware and its management in Visual Cloud. Now Intel is unleashing innovation in Visual Cloud. It is a total solution in different scenarios, such as media processing and delivery, media analytics, immersive media, cloud graphic, and cloud gaming. Include encode, decode, inference, and render. This is a media analytics pipeline. It should go through decode, inference, and encode process. The Visual Cloud is a full stack, include hardware and software. The hardware covers different domains in computing, storage, and networking, such as Xeon processor, VC card, IPG card, Optane persistent memory, graphics card, and movie DAS. The software includes different tools in encode, decode, inference, and render, such as media, server studio, WebRTC. OpenWindow, Media Display SDK, and other render tools. Besides these tools leverage AVX512, WebRTC can also leverage VC card, and OpenWindow can also leverage FPGA. Now let's see how this hardware power 8K video processing. This is Intel Xeon Scalable processor. All Xeon processors support AVX512. With mesh architecture, it delivers low latency and high bandwidth among cores, memory, and I/O controllers. Thus, performance of video stitch, encoding, transcoding, will be greatly improved. This is the Optane family, include DC, persistent memory, and SSD. They are high performance in bandwidth, IOPS, and latency. You can see it's more faster in endurance and denser than conventional storage medium. This is the Intel FPGA. The new product is Strategic 10. It supports high floating point performance, high speed transceiver, high bandwidth for parallel memory interface, useful in inference and HPC. This is QAT. It provides hardware acceleration for computer-intensive workloads, such as data storage and transmission. It supports 100 GBS cryptography and 100 GBS data compression. This one is a smart NIC. It's used for network acceleration. Currently, it supports 225 Ethernet. It supports full Open switch acceleration. It is programmable and easy to deployment. Here is the status of some accelerators in upstream. Now we have support FPGA in Cyberger. With Cyberger, we can discover FPGA and program it. And I think we have seen the Cyberger FPGA demo in the keynote. The QAT, crypto, and compressor already supported in Ceph. Percent memory spec is under review in Nova. And we are supporting persistent memory for read and write cache in Ceph. LibreOS supports VNAI, the new ISA for inference. Kubernetes has already supported QAT, GPU, and FPGA. All FPGA, GPU, QAT plugins can be run as a daemon set. All these accelerators can be shared by multi-pods. For FPGA, it supports two modes, AF and region mode, but it does not support image management. For QAT, it needs to preload and configure DPDK driver, pre-install and configure Quick Assistant Technology software. So let's see Cyberger. Cyberger will support more management for these accelerators, such as dependent software management and FPGA image management. The community are trying to make integration with Kubernetes. There will be a Cyberger master plugin run in Kubernetes master and a Cyberger node plugin run in Kubernetes nodes. All they are containerized. And leverage customer resource definition to extend Kubernetes to support all these accelerator function. Okay, that's all from me. It's time for demo.
Okay, before the video demo, let's take a look at the environment. We have a data center side and one edge cluster. The data center is managed using the ThinCloud OpenStack, while the edge node have one GPU and the cameras and other devices connected.
Okay, let's start our demo 1. It's a short movie. First, log our ThinCloud OpenStack product. After that, let's go our physical topology page. A few seconds later, we can not only see the data center physical topology, but also get the edge clusters topology. At the data center, we can see the switches and servers and their information, such as system and running status. At the edge, we can also see the switch and the server and their information, such as system and running status. At the edge, we can also see the switch and the server. Additionally, we can see 5 devices from different vendor with different color, which attached to the server. So this is we have done in physical topology management, and we still have a lot of work to do. Let's show our demo 2.
Okay. This video is going to demonstrate have 2 groups of comparison, and the first we compare the video process. We compare the process to accelerate 8K video. So not only the encoder decode process, but also the detection process. So this video is going to demonstrate that So we first check the resolution of our video using the FM pack, and then we change to the DuckNet. And the DuckNet is a neural network framework, and which is and we also use UNO. UNO is used for object detection. So we check the UNO config and see different parameters. This video where you can see the people from left to the right. After we use GPU to encode, decode as well as detection, it's much faster than the rest. And the video in the middle, we decode using CPU and use GPU to detection. And because and this way is utilized by the darknet code right now. And in the right is the process of using all CPU. So we find that the FPS of all GPU is at 25.4. And in all CPU scenario, the people are almost stable, static. And the FPS of the middle video is 10.4. And for the all CPU, it was very small, yeah. And here we, and this is another comparison because we use the 8K video as the input, as well as use the 1080p video as the input, and we get the output after running the darknet and compare these two videos. First, also check the resolution. And we using the darknet, we get the output video. Also, the output video for 1080p. And the video at the top is we using the object detection for the 8K video. And the video in the left is the output of we using 1080p video to do the object detection. And you can see there are more details and more objects have been tagged from the top of the video. So let's go back to the slide. And this is some information about the object detection. We use darknet and the UNO V3. And we also do comparison, two-group comparison. So this session, we are talking about our age-optimized architecture based on Starling-X. And our architecture and our solution can manage a device and a network topology as an age, and also manage different accelerators via Cyborg. And the video demo shows that the 8K video is much more can provide much more details in analysis. And for the real-time analysis, that 8K video should be accelerated in every processing procedures, not only the detection, but also the decode process. So, and there's something about the future work. We want to containerize the Cyborg and use the user space network stack to accelerate our edge networking. So it's the QA part. Do you have any questions?
If all of you have any questions, you can connect us by calling the connection. Thank you. Thank you so much.